Anybody has any question? No? Yes. We did not really go on the detailed protein composition, the detailed recombination complex, but know for this class, know overall how it happened, correct? If we go into the detail of the specific function of the protein, we go really in detail of the recombination. Okay. So we have exam next week, Tuesday, correct? So last class, I think we finished the transcription, correct? And we will start protein synthesis, and so we have discussed how exactly the DNA is duplicated into, correct? The DNA, which is replication, and then we discussed how DNA is transcribed into RNA. So now, once we make the RNA, we need to make the protein. mRNA, which is the messenger RNA, which codes for the protein. So DNA to RNA, and RNA acts as template for the synthesis of the protein. And in this section, we will talk about how mRNA is translated. This process is called translation. How mRNA is actually translated into different proteins. So something called genetic code. You have studied somewhere about the genetic code. So we have 4 different nucleotides in RNA, and these 4 nucleotides can be, correct? They can form different permutation combination, and normally 3 nucleotide sequence consecutive 3 nucleotide sequence, like let's say AUG. We are talking about the RNA, so that's why we are using AUG. And this AUG is a triple letter code of the RNA. This codes for a particular amino acid, and AUG codes for methionine. Okay, like UUU, all U, correct? UUU codes for, it codes for phenylalanine. What is the single letter code for phenylalanine? A, correct? So these 3 letter codes for phenylalanine. So these 3 letters conjugative letters. This code for a particular amino acid is called genetic code. Okay, so mRNA has the sequences. It has different sequence A, U, G, and all kinds of nucleotide sequence. And these AUG actually the starting amino acid, start codon. The first in bacteria, especially in prokaryotes, the first three letters is AUG. Wherever if you have big mRNA, if you have a big mRNA, you have wherever you find AUG, you would consider that this is the start of the protein sequence, not the transcription start site. Transcription start site may be further upstairs. So, if this is your DNA, then the transcription start site was there. Does it make sense? And you had a transcription stop site there. So your RNA is this big because it has transcribed the big RNA. In prokaryotes there is no processing. In eukaryotes you are processing. So this is a big RNA, and this is the beginning 5' end. Does it make sense? But it does not. Translation, the protein synthesis does not start place from the beginning. Rather, it starts where it is AUG. That's where the ribosome first recognized. Does it make sense? And sometimes stop sign, this is translational stop sign, and translation stop sign maybe here something called PGA is a stop codon. So actual protein is only this one. Does it make sense? Yes? It could be TGA also. Yeah. Oh, you mean the T for you? Yeah. I am always thinking about you. Okay? I have to confirm. Anyway, we'll talk about this. TGA in the DNA, so it will be UCT. I'll check about it, okay? So, is the concept clear that you have a big mRNA, transcription start site, by transcription start, correct? You make a big RNA, this is the transcription stop site. So, your RNA is from there to there, but when it is protein synthesis, it may not be starting from the beginning. Normally, it does not start from the beginning. Protein synthesis starts at AUG, which is a start codon. Does it make sense? So, sometimes this particular sequence is 5' untranslated region, very common in eukaryotes. Same, it will be 3' untranslated region. Does it make sense? This untranslated region of the RNA is very critical. Although it is not translated, it is also critical for the function, stability of the RNA, and may be influencing the translation process as well. Does it make sense?
Is there a condition where the AUG is like the very first one of the 5' end? Could that be a possibility?
So there,
Yeah.
normally it does not happen.
Okay.
Okay. But if it is there, it will start from there. Sometimes you will see another AUG here. What it means? It may be another start site. So protein could start here. We will talk about something called frame, in frame and out of frame. AUG has to be in frame so that it codes for an amino acid. Correct? What I mean, let's say AUG C A U G, something like that. This is an RNA. So first start site is here, translation start. Does it make sense? So this is 3 nucleotide. Yes? Next 3 nucleotide is CAU. So it will be methionine, and whatever the amino acid next it will come here. But you have AUG there. Does it make sense? But this AUG, if this is the start codon, this AUG is out of frame. Does it make sense? Yes or no? So sometimes the sequence, you have a big DNA sequence, for the translation, being in frame is the most important. Correct? Although you have AUG, this does not code for methionine here because your code is PAU and G goes to the next frame. Does it make sense? Now, let's say you do something, mutate this one, delete this C, you could do the mutation, a single base there you could remove, correct, synthetically. Then or mutation. So you will produce AUG, A, C, AUG again. So this is a frame, in frame. Now here CAU was one frame. But now the frame is changed to next AUG. Does it make sense? So there is a shift in the frame. Does it make sense? So you will end up with a different amino acid if there is a deletion mutation. Deletion mutation will cause normally frame shift. If there is 1 or 2 base deletion, if there is 3 base deletion, you remove one amino acid, but they are still in the same frame. So some of these concepts will come. This is a frame shift mutation. Okay? So AUG is the beginning code, and we have 4 different nucleotides, and these 4 nucleotides can be combined into different permutation combination of 3 nucleotide set, correct? So let's here UCAG, we orient them UCAG. Okay, you can make all these different combinations. You could have U and you have here another combination. Say UCAG. So you could have U, correct? You could come and have another combination U, C, other U. So 4 nucleotide is changing here. Does it make sense? So U, and 4th one is UCAG. You are changing. So there are 4 possible combinations here. U, and then 4th one is changed. So for each nucleotide, for this one you could do UC, UCC, and UCAG. So for each 2, we have 4 different combinations. If you do all these combination of 3 sets out of these 4, you get 64 different combinations of 3 nucleotides. Does it make sense? So in the 60s, 1960, correct? People already know that DNA is a double helix, correct? We know 1957 that DNA can be replicated using DNA polymerase 1 discovered by Arthur Kornberg, correct? Father Kornberg. So, you know how to replicate DNA. There are plenty of supporting evidence that yes, DNA acts as the genetic material and somehow it has connection to the protein, correct? So, but people did not actually experimentally demonstrate what is the real connection. We know that there is protein. This is 1816 by Mendel, correct? He said that you have alleles, correct? Alleles are eventually, alleles means now we call them what? What is actually allele? It's a gene or gene sets, correct? So it could be one gene, but it could be a set of genes which are responsible for a particular phenotype, correct? So alleles dictate the phenotype, allele dictates the protein, but there was no molecular link demonstrated that DNA, how exactly it translated into protein. Does it make sense? The DNA to RNA is done, transcription, RNA to protein, it's there, but still people are not so sure, correct? Then Nirenberg, Nobel laureate, who discovered the genetic code along with Carl Gobind Khorana and another scientist. So three people got Nobel Prize. So Nirenberg was a biochemist, and he was trying to understand how exactly RNA codes for protein. Does it make sense? So what he did, he took the E. coli cell extract. Why cell extract? Because you don't need to purify any protein. Cell extract is all the protein which is required for the cell. Does it make sense? So he fed certain RNA molecules to these nuclear, not nuclear extract, cellular extract. And the first one he fed the cells is actually poly-U. Poly-U. So polymeric uracil. So you take the cell extract and add this polymer. Does it make sense? And it has some amino acids and everything is there. And what he found, when he supplies this poly-U, it gets a polymeric protein, and which is phenylalanine. Does it make sense? So his conclusion was that this polymeric U sequence codes for phenylalanine. Does it make sense? And this was the first genetic code discovered by Nirenberg. Now he is a biochemist, a fantastic scientist. Biologists are fantastic. Everybody is fantastic. Who is not? Correct? You are also fantastic. I am also. Not so. Correct? So he was fantastic in biology, biochemistry, but he was not a fantastic organic chemist. So now that he showed that U codes for phenylalanine, now he knows that there are other possible combinations. You see all different, the 64 different combinations are possible. Now he was dreaming, if I could feed this particular acid instead of UUU, other combination of the RNA. Does it make sense? Then you could actually figure out if you feed this particular RNA what you are going to get. Does it make sense? So he took the help of a famous organic chemist, Hargobind Khorana, and Hargobind Khorana at that stage he was famous for his nucleotide organic synthesis. Organic synthesis very well developed from 1800, late 1800, early 1900. Okay, Nobel Prize for any complicated organic molecule you give, these people will make it. Even today, much more advanced chemistry, so all complex natural products, people will make it. You make it tiny. Sometimes it takes 30 steps, 40 steps, but organic chemists are like God. They create molecules. Okay, synthetic organic chemistry. They can create new bonds, correct? What are we human? Nothing other than combination of couple of atoms and bonds, correct? So that has been created by somebody else, hopefully. I don't want to get into that argument. But if organic chemistry is creating new combination of atoms, so what would you call them? What? Right? I am an organic chemist by training, but not so close to God yet. Correct? So, Hargobind Khorana was the organic chemist. His expertise was to synthesize this dinucleotide, trinucleotide, tetranucleotide. Anything you ask him, can you make AT? He said yes, I can make. And in test tube, in round bottom flask, he could make any combination of DNA. But today you don't need Hargobind Khorana because a lot of automatic machine is there. You type the sequence ID that you AUG, okay, supply the reagent, 1 hour later, you have all these nucleotides coming out of the machine. And in fact, if you want to get 20 nucleotide, long RNA, DNA especially, you can get in $2. Sigma. Okay? I tell my students, as many oligonucleotide you need, just order. Right? If there is no money on the grant, I can pay it from the pocket. Just $2 you can buy any nucleotide, you can clone any gene. And that is possible because organic chemist has developed in solid phase, first solution phase synthesis and then solid phase automation. Does it make sense? But in 1960, there was no automation. We have to make this molecule in test tube. Correct? You have to take the expertise like Dr. Lovely is not a part. Correct? Dr. Lovely is total synthesis but not nucleotide. But Khorana was expert in nucleotide synthesis. Nirenberg contacted Khorana and said, I have this problem, I need different combination of nucleotide, can you make? Khorana said, yes. Correct? He made all different combination of the nucleotides, trinucleotide combination, and Nirenberg fed his acid. Right? So if you give poly U, you get phenylalanine. If you give UUC, you get phenylalanine. But if you get something else, right, like GCU, you get alanine. So basically, it's a combined effort, a strong biochemist, a strong organic chemist, eventually elucidated the complete genetic code. Okay, how 3 nucleotide sequence dictates a particular amino acid. Mechanism is later, correct? That is the discovery of genetic code. And I think among many Nobel winning discoveries, like you can say that to me, Earlier is Charles Darwin, Mendelian genetics, discovery of antibiotics, correct? Alexander Fleming, penicillin, and then discovery of vaccine, I think, is very important, which saved a lot of people. Then DNA doubling, correct? Watson and Crick. Then lot of correct good discovery. Among those, I think DNA replication, discovery of genetic code is another milestone, because it really is a milestone. It shows you how mRNA is connected to protein. Correct? So this is the discovery of the genetic code. So 3 nucleotides, the take-home message is that 3 nucleotide, consecutive 3 nucleotide code for a particular amino acid. If it is UUU, this is the first genetic code discovered. This is phenylalanine. Okay. If it is AUG, where is AUG? AUG, A, U, and G. AUG is methionine. Okay. And some of the genetic code, so there are 64 different genetic codes, but only 20 different amino acids, correct? So some genetic code, more than one genetic code, one sequence code for one amino acid. And there are 3 codes which does not code for a protein. These are called stop codons. These are used as stop codons because it does not code for an amino acid. If the translation machinery goes there, it stops there. So it is used as stop codon. Does it make sense? So where is the stop codon? UGA, yeah. UGA is a stop codon. What did I write there? UGA. So that was right. Okay? UGA is a stop codon. There are 3 other stop codons, UAA and UAG. So here you see UUU, UUC, just U to C conversion did not change the amino acid. So first 2 letters, it's very complex. We are not going that detail how exactly this genetic code dictates a particular amino acid, but you can see that UUU as well as UUC, this codes for phenylalanine. UUA and UUG codes for leucine. Okay, so sometimes what it is telling that sometimes more than one trinucleotide sequence, more than one correct genetic code codes for it, codes for the same amino acid, because you have 64 combinations, you have 3 stop codons, so another 61 codes for 20. Does it make sense? Yes or no? Yes. So for your exam, I don't expect you to remember all 64 genetic codes unless you want. Correct? It's not a bad idea. Okay, if you don't want, no. But I do want you to know a couple of them. Okay, let's know the first one, UUU, phenylalanine. Correct? You know AUG, why is AUG? Methionine, because you will be reading them now and then. Correct? You also need sometimes stop codon for cloning, etc. I normally remember UGA. Okay. UGA. So if you find an RNA, there is AUG and UGA, and they have to be in frame, then you can predict what is the start site, correct? what is the termination site, end of the protein. Yes or no? Correct? But they have to be in frame. If they are out of frame, then genetic code is different. Correct? So this is the discovery of genetic code. Is it clear what am I asking you to remember? Yes? Okay. So let's see if I want to remember anything else. So the first genetic code, phenylalanine, AUG, methionine, start codon, and stop codon. I can say which of the following genetic code acts as a stop codon. Right? I give multiple combination, so multiple choices. Does it make sense? Okay, so this is the genetic code. This is what it is telling is that overlapping genetic code, that means it is very different frame. Correct? Three nucleic acid bases here, 3 nucleotides. This is one frame, but the second, third, and fourth, that also could be a frame. Does it make sense? Any 3 nucleotides could be a frame. So there could be multiple different overlapping frames, 3 different overlapping frames, correct? So this is non-overlapping. 3. So this is non-overlapping genetic code 1, 2, 3, 4. So each of them will be translated into one amino acid, one after another. We discussed this, that frame. Now that we know that if 3 different amino acid combination, you get different protein out, and you know that you need 3 nucleotides for a amino acid. Now the question is, what is the mechanism? Correct? How exactly RNA is matched to a particular amino acid? Correct? And how the translation process is taking place. So there comes your tRNA. Okay, so the mRNA acts as a template. tRNA acts as a kind of matchmaker. Matchmaker, right, is not so common here. Matchmaker is a kind of person who, correct, is the marry of two boys and girls, right? In India or some of these places earlier days, a boy will marry a girl whom they don't know each other, right? Which is good or bad, I am not going into that discussion. But matchmaker is the person they have to match. This is the perfect match for this boy and this girl, and I don't know how perfect it is. Correct? So tRNA actually acts as a matchmaker. Okay? It brings the mRNA and it brings the particular amino acid which needs to be aligned up for the protein synthesis. So tRNA actually matched with its amino acid is matched with its proper tRNA. So each amino acid has a specific tRNA. Okay? So tRNA is this one. We'll go back to those slides again. Let's introduce the tRNA a little bit. So this is a tRNA. I think this is the phenylalanine tRNA. Okay. this has this type of structure. Most of the tRNA has, I think, 74 to 95 nucleotide long bases. So less than 100 nucleotides. Know the length of the tRNA. Okay, they have this type of structure. Okay, contributing RNA is primarily correct. Single stranded, no. Actually, RNA has lots of secondary structure, and these regions are of course complementary. That's why they form duplex, and these regions are not complementary, so they form loop probably like structure, cloverleaf structure. Okay, so this is the typical structure of an RNA, tRNA. You see that these are the different structures of different tRNA. This is the phenylalanine, that's what I showed up here, correct? This is the phenylalanine structure, this is methionine tRNA. So they have this structure. This is serine, this is alanine. Sometimes these arms, variable arms, are shorter, longer, and so on. But what is conserved is its structure, and like this type of structure. This is your 3' end, this is 5' end. These are the variable arms, so length could vary, and sequence could also vary to some extent. And this end of the RNA has 3 letters complementary to a particular genetic code. Okay, if genetic code is AUG, then the complementary will be what? U A, correct? C. Is it clear? So this sequence will be that complementary sequence, and through this complementary sequence, this is called anticodon, because opposite to the codon is anti, correct? So this is your genetic code, this is the code. So this particular region, this 3 nucleotide will see, okay, these are the complementary to the genetic code. Okay, so they have a conserved structure about 70 to 95 nucleotide long. They have a 3' overhang. This is the 3' end, and they have some variable region loop which could vary for depending on the amino acid. And this particular region has a complementary sequence to the genetic code. Okay, so this is the typical structure of, this is phenylalanine tRNA. We have this thymine pseudo. This is anticodon loop. Anticodon loop. Why it's called anticodon loop? You now make sense, because this is complementary to the genetic code. Does it make sense? This is the variable loop. So depending on the RNA, depending on the tRNA, for each different amino acid we have a different tRNA. So for each tRNA, something has to be different. So these are the variable regions, correct? And we have a 3' overhang, and this 3' end of the tRNA is actually connected to the amino acid specific to that particular tRNA and specific to the anticodon or codon pair. Does it make sense? Yes or no? So this here 3' end is connected to the amino acid. If it is phenylalanine, okay. So it will be, what would be the anticodon sequence if it is phenylalanine? It will be AAA. Correct? A because it has to bind to the U. Does it make sense? And if this is A, of course the other sequence is conjugate for that particular amino acid. This 3' end of this tRNA will be connected to phenylalanine. Does it make sense? If it is methionine, you will have different tRNA. So this is a connection. So 3' end phosphate group. This is a 3' end A. I think the sequence is CCA. Let's look at it. Yeah, 3' end sequence is CCA. This adenosyl group is connected to the amino acid through an ester linkage. So this is the tRNA. The sequence of the 3' end of the tRNA is CCA. Is it clear? And this adenine group, this is the adenine group, last adenine group at the 3' end. This is the 3' hydroxyl group is forming an ester with the carboxyl group of the amino acid. Is it clear? Yes or no? So the amino acid carboxyl group reacts with 3' end adenosyl group at the 3' end forms an ester linkage. So if it is adenine, if it is phenylalanine, if I ask you to draw the phenylalanine attached tRNA, what would you like to draw? Correct? I am asking phenylalanine specifics. Specific tRNA. I am not asking you to remember the whole sequence of the tRNA unless you want. Correct? But at least what I want you to remember, because this is phenylalanine, you know what are the sequence of anticodon. Is it clear? So what is the sequence? AAA. Correct? Now, last sequence here CCA, 3' end. This is 5' end. This is 3' end. And adenosyl group A. These are phosphodiester there, correct? These are ribose. These are RNA. Now this 3' hydroxyl group of ribose sugar connected to the phenylalanine carboxylic acid group. What is phenylalanine? CH equal to H, HCN plus, and we have CH2. Am I correct? This is phenylalanine. this phenylalanine, this carboxyl group reacts with this hydroxyl group and produce CH NH3 plus Is it clear? Did I do it right or wrong? Yes?
Yes.
So this is the phenylalanine specific tRNA, which is, if you bring a different tRNA, your anticodon will be different, and this group is the amino acid which is matching with that genetic code. Is it clear? So this is called 3' O amino acyl group tRNA. Amino acyl tRNA. Does it make sense? Yes or no? There are certain rules for codon-anticodon pairing. We are not getting into detail, but codon-anticodon must have to pair. Correct? If you have a large RNA, you have a large RNA, you have genetic codes, correct? These are genetic codes, triplet. This is AUG, the first codon, start codon. Basically, all it does is brings anticodon here. This is, what amino acid is this? Methionine. Alright? For the next one, you bring another amino acid, let's say phenylalanine. So you bring it, correct? So because they have codon-anticodon pairing, this sequence comes and sit down complementary on the mRNA sequence. Once you have that, next job just form the connect these amino acids. Amino acids are connected by peptide bond. So you need to catalyze the peptide bond between these two neighboring amino acids. The next sequence, once this is done, next RNA comes, you make peptide, next comes, you make peptide. So peptide translation, initiation, elongation, until you find UGA which does not code for the protein, which is stop codon. Does it make sense? Eventually, you synthesize the peptide. Okay? So codon-anticodon pairing is critical. There are certain rules. The first two letters stronger in terms of what amino acid it will bring and so on. We are not going into detail of these rules, but codon-anticodon pairing is important. Some codons are used more than others. Okay? So whole this process, all of this process takes place in the protein synthesis machinery. which we call ribosome. Correct? So ribosome takes care of these reactions. Before that, I possibly want to go little something else. Let's see. Okay, here. So there are different amino acids, 20 different amino acids, and 20, there are at least 20 different tRNA, because for each codon you have tRNA, correct? So how is exactly tRNA know that which amino acid it will bring? Because this codon anticodon does not see the what amino acid is here. Does it make sense? Whichever amino acid this tRNA will bring, that will be connected. Codon anticodon binds to the tRNA, not the amino acid. Does it make sense? So instead of methionine, if you load some other amino acid, still translation will go because it does not distinguish. Does it make sense? So there has to be a mechanism by which a particular tRNA is connected or loaded with a specific amino acid. If it wrongly brings a different amino acid, then you will have wrong protein. Does it make sense? So how is an amino acid matched with its proper tRNA? There is an enzyme, family of enzymes which are called amino acyl tRNA synthetase. Synthetase means they require ATP. Does it make sense? So amino acyl tRNA synthetase actually brings the tRNA, brings the amino acid, and form that ester linkage between the amino acid and 3' in hydroxyl group of the adenine, the 3' end of tRNA. Does it make sense? And amino acyl tRNA synthetase discriminates between various tRNA and amino acids. So there has to be different amino acid tRNA synthetase. So this is how it reacts. You have an amino acid, let's turn on this side. You have an amino acid, you have tRNA, you have ATP, correct? I did the reaction. Did I draw the reaction? Yeah. Let's turn on the light. So here is your reaction. I think we had another duster. I have to just run this side and that side. Okay, so let's erase this part because this part, you know. Now you have to. This is tRNA, 3' of the tRNA, correct? So this has to react with this carboxylic acid group. Of course, this reaction is catalyzed by tRNA synthetase, which will form the ester group between this and that. Now, why you need ATP? It requires an ATP. What is the function of ATP? Activation of what? Activation of this carboxyl group. Correct? Carboxyl group is not active. This has to act as a nucleophile to the corresponding Actually, it stays at minus, so it's more difficult. It cannot attack this. So this will not happen because O minus is extremely poor living group. Does it make sense? So that's why this group, we have done the ATP activation many times. Do I need to do the reaction? Carboxylic acid reacting with an ATP. Alright? So sometimes, I have too many. Correct? Yes or no? So this can react with this one. Sometimes it also reacts with alpha, but it depends on enzyme. Eventually form an anhydride type of linkage. I don't know which one reacts here. It may be the alpha instead of gamma. But the goal is to make this anhydride linkage, whether this phosphate or this phosphate, that depends on the enzyme. Correct? Now we have made an activated, this carboxylic group is activated with a phosphodiester bond, or sorry, phosphoanhydride bond. Now this can react. Is it clear? So ATP is required to activate the extremely poor nucleophile, I mean the living group in the carboxylic acid. Is it clear? Any questions? So I did the wrong linkage, so it does react with the alpha. Okay? So it does react with this one, okay? So you will produce Is it clear? Did you figure out my mistake? I initially made the phosphorylation here, but it reacted the alpha phosphate. We form ADP, ANP derivative. Does it make sense? We produce the phosphoanhydride linkage. Now this hydroxyl group reacts with the activated carbonyl group and lose ANP. Is there any problem? Is it clear, everybody? So you produce this ester amino acylated tRNA and releases AMP as I mentioned one of us. Is it clear? Yes or no? So this reaction is catalyzed. All these reactions, of course, you need to also decrease the pK of this hydroxyl group. Right? For the nucleophilic atom, you need metal ion. You need the amino acids present in the active site of the enzyme so that, right? This hydroxyl group has reaction. Let's turn on the light. Can you see, or let me increase the size? So you have the amino acid. Can you see now? Yes or no? So you have the amino acid. This group is activated with ATP. So tRNA, proper tRNA comes, it matches, it needs amino acid tRNA sequence, it needs ATP, you need magnesium ion. What is the function of magnesium ion?
Stabilizes.
Stabilize what? You are not wrong. So what is the other function? What is the other function of magnesium? See, eventually this hydroxy, what is it? tRNA. The tRNA 3' hydroxyl group what I draw, correct? So you have produced carboxylic acid ATP, you produce, correct? This carboxylic group attached to the alpha phosphate of the ATP, so you form this phosphoanhydride type of linkage, correct? Phosphocarboxyanhydride, yes? And then this group reacts with this hydroxyl group of the tRNA, 3' and adenine group tRNA, correct? So this hydroxyl group has to react with this activated carboxylic acid group, carbonyl group, so that you can form that ester, acyl linkage. But what's the pK of this hydroxyl group? Somebody said. So, what is the pK of that hydroxyl group? Okay, multiple charge? 2. Okay, 2, 10, 13, and 17. What is the pK? It's about 13. It's not 10. 10 is phenolic OH hydroxyl. Actually, not 13, it should be in the range of 14. Okay, it's higher than 13. It should be 14. Correct? It's alcohol. Now, so it's not a good nucleophile. You need to make it as a good nucleophile. At physiological pH, they need metal ion coordination. That's why you need metal. Metal to activate the enzyme. Decrease the pK of this one. Of course, stabilize the ATP as you said. Does it make sense? So ATP is required to activate the carboxylic acid of the amino acid to form this A and P derivative. Now the tRNA hydroxyl group, 3' hydroxyl group, reacts with this particular one. We lose A and P and form this amino acid tRNA. So this is catalyzed by amino acid tRNA synthesis. There are two types of amino acid tRNA synthesis, class 1 and class 2. The difference is class 1, it's all same. In class 1, initially this 2' hydroxyl group reacts with this amino acid, so to form a 2' derivative. Eventually it needs to be 3' derivative. Amino acid, incoming amino acid must be acylated at the 3' hydroxyl group. Okay? So class 2 does directly, class 2 do in 2 steps, class 1. Does it make sense? Yes or no?
Mm-hmm.
So now you have made the amino acylated tRNA. This is called charged tRNA. I mean, amino group is charged on this tRNA. Now, how does amino acyl tRNA synthetics the enzyme knows that which tRNA will be matched with which amino acid. Correct? If tRNA, so amino acid tRNA synthesis, enzyme is the one which really matches the RNA and the specific amino acid. How does it match? Very good. So basically what you are telling, you are right. It's not only variable, total RNA. So tRNA synthesis is an enzyme. It has binding sites for both the tRNA as well as specific amino acid, correct? So a specific tRNA synthesis which is specific for, let's say, phenylalanine, it has the ability to bind specifically the phenylalanine specific tRNA and the phenylalanine. Then connect. Does it make sense? So tRNA synthesis actually determines which amino acid will be matched to which tRNA. That's why people say that it's a second genetic code. Because if it does a mistake, even if you have this genetic code, it doesn't matter. Does it make sense? So tRNA, amino acid tRNA synthesis does play a critical role in matching the specific tRNA with the specific amino acid. Is it clear, these concepts? Couple of concepts, those are simple but those are important. Correct? You have tRNA, you have genetic code, tRNA has specific structure. Amino acid tRNA synthesis connects a specific tRNA with an amino acid. So now you have different tRNA loaded with different amino acids. Does it make sense? Yes? So next is connecting the amino acid. Yes?
So is the amino acids already loaded onto the tRNA before it's binding to the mRNA?
Yes. So then it binds, we'll talk about this one next class, how ribosome helps synthesizing another Nobel winning discovery. Okay. And so you are forming a peptide bond, correct? You need an enzyme. Normally we know that enzymes are proteins, correct? But in this particular case, these peptide bonds are formed by enzymes which are called peptidyl transferase, and they are not protein, they are actually RNA. Okay, this is called catalytic RNA. Nobel Prize, I think Tom Sheck, 80s. This is the first time he demonstrated that tRNA synthesis, not tRNA synthesis, the peptidyl transferase, which makes up peptide bond, is not a protein, it's an RNA. So it's called catalytic RNA. RNA is able to catalyze the peptide bond formation. Does it make sense? We'll talk about that next class. So how about in your next exam we cover up to whatever we discussed today. Okay? Next class, whatever we teach, we will also review. Correct? That can go to the final. Okay?